In the phase-to-phase-to ground fault, the voltage will fall in the two faulted lines, and a heavy current will circulate in these two lines and also to ground. With a single phase-to-ground fault, the voltage of the faulted line to ground will fall close to zero at the fault location, and heavy fault current will circulate through this line and return through the earth to the grounded neutral. The resistance of the fault itself plays an important part in determining the value of fault current. Indeed, if this is very high, there may be insufficient fault current flowing to operate the relays. All of the faults that we've been studying so far involve short circuits. There are other abnormal conditions arising from open circuits, but these are far less common. Let's look at a typical example of one phase which is open-circuited. And this case will serve to introduce the term ferroresonance. You'll remember from your study of electrical fundamentals that the term resonance refers to the combination of inductance and capacitance that can give rise to extremely high voltage levels. For example, look at this simple series circuit. We have an inductive reactance of 2400 ohms in series with a capacitive reactance of 1600 ohms. The voltage across the circuit is 8 kV. The resistance of this particular circuit is negligible. Therefore, the total impedance of the circuit is 2400 minus 1600 equals 800 ohms. Remember that capacitance and inductance have opposing effects. So the value of current through the circuit is equal to 8,000 volts divided by 800 ohms equals 10 amps. But what is the voltage drop across the inductance only? Well, here we have 10 amps times 2,400 ohms equals 24,000 volts. Similarly, we have minus 16,000 volts across the capacitance. So although only 8 kV is applied across the total circuit, we have very high voltages in individual parts of the circuit. And this is precisely what happens when we have ferroresonance in the power system. Typically, this can occur where we have a delta-connected primary of a distribution transformer. In this system, the distribution line is being fed from a Y-connected secondary with the neutral grounded. As this is a distribution line, fuses are often used, so let's consider the situation where one fuse only blows, such that we have one phase open-circuited. This situation can also occur where the lineman opens feeder switches one phase at a time. In the interim period, the transformer is still connected to the other two phases, and currents will circulate in this manner. The return path to ground is through the capacitance of the open line. So now look carefully. We have inductive reactance in the transformer windings in series with capacitive reactance between line to ground. Depending upon the specific values of capacitance and inductance, a very high voltage could arise across the transformer winding and also from the line to ground. This could damage insulators and the winding of the transformer itself. This condition is more likely to occur where voltages are 12 kV and higher, and also where the line capacitance is high, for example with long lines or where cables are used. When you think of all of the variables in the circuits, this subject of ferroresonance is obviously highly complex. But it is essential that we understand the principle, because we shall be meeting this term in future tapes when we discuss specific installations. Clearly, in designing the power system, the engineer tries to ensure that specific values of impedance and capacitance will not lead to resonant conditions. Incidentally, you may have already perceived that one way of reducing the resonance effect would be to insert a resistance in the neutral of the source transformer. But didn't we already point out that we prefer to have this neutral solidly grounded? This is yet another example of opposing interest and compromise that we often meet in power system design. Well, at this point, we all deserve a well-earned break. It is essential that you become familiar with the concepts presented in this tape to assist in understanding the specific protection schemes that are discussed in later tapes. Please switch off the tape now and take time to thoroughly review this material in your workbook and then go through the questions. In the last segment, we used phasor diagrams to show how conditions at a fault location become distorted from the normally balanced voltages and currents. The phasor diagram is really a geometric or mathematical representation. We're now going to use another mathematical representation and break the phasor diagram into symmetrical components. This allows us to go a stage further in our analysis of fault conditions. As we already know, under normal operation, the power system is balanced, and there is a symmetrical relationship between the three-phase voltages and currents. Even with a three-phase fault, phase quantities remain 120 degrees apart. This symmetrical relationship helps simplify the calculation of currents and voltages under these conditions. However, when the system is unbalanced, analysis is more complicated. We need to divide the voltages and currents into balanced sets of symmetrical components. Let's look at this a little closer. To begin with, we already know that a generator produces three equal voltages, which are equidistantly spaced 120 degrees apart. We have also already pointed out that the phasor rotation is conventionally counterclockwise, and the normal phase sequence is A, B, C. This means that for any fixed point in space, we would see voltage A, then B, then C, then A, and so on in that sequence. When studying symmetrical components, phase voltages are always used, that is, line to neutral or line to ground. We indicate the positive sequence voltages on our diagram by using the subscript 1. For example, VA1, VB1, and VC1. With a balanced load, the current phasors produced by the generator are also similarly balanced. They'll look like this, once again marked IA1, IB1, and IC1. For study of balanced faults, such as a three-phase short circuit or three-phase to ground, only these positive sequence components are needed. But what about unbalanced faults, such as a phase-to-phase fault or a phase-to-ground fault? Well, as we'll see, other components are needed in order to analyze these unbalanced system conditions. Let's look at the phase-to-phase fault where no ground is present. The fault is between line A and line B. This voltage phasor diagram shows the conditions at the fault. The phase voltage on line C, that is VC, remains at its normal angular displacement, but A and B have been brought closer together by the low impedance of the fault. Now, remember, the generator, as always, is still producing positive sequence phase voltages. But at the fault, the voltage phasors look like this, with the different phase voltages being identified by VA, VB, and VC. The voltage at the fault on the unfaulted phase is approximately equal to its pre-fault value, and with our phase-to-phase fault, the positive sequence fault voltages are about 50% of this. How do we get from here to here? Well, obviously, other voltages are present at the fault and are being imposed upon the positive sequence voltages. That is, other voltage phasors must be added to the positive sequence phasors to get fault phasors. We can find the missing components by carefully studying the phasor diagram and adding appropriate phasors. Now, to transpose positive sequence fault voltage VA1 to VA at the fault, a phasor must be added in this direction. Let's call this VA2. Similarly, to transpose VB1 to VB, another voltage, VB2, is at play. And observing carefully, we see that the voltage VC is actually greater than VC1. Another voltage phasor, then, VC2, has to be added to produce VC at the fault location. Now, if we bring all of the transposition voltage components together, we find that they are equidistantly spaced at 120 degrees apart and are of the same magnitude. But look carefully. Considering conventional counterclockwise phasor rotation, the phase sequence is reversed. From our point in space, we will now see phase A, then C, then B, then A, and so on. Just the opposite to the positive sequence, which is A, B, C. So this is known as negative sequence, and the values are normally given the subscript 2. This brings us to a very important